You live on a planet so small that more than 1 million copies of it could fit inside the Sun. That Sun is one of 400 billion stars drifting through a galaxy so enormous that light itself needs 100,000 years to cross it. But none of that prepares you for what sits right next door. Just 2.5 million light-years away, a galaxy called Andromeda stretches across 220,000 light-years of space and contains roughly 1 trillion stars. It dwarfs everything we call home, and right now, it is heading directly toward us. What follows is a journey through measurable distances so extreme they will systematically dismantle every intuition your brain has ever built about size, distance, and where you actually stand in this universe. If you enjoy having your perspective on reality completely reshaped by real science, do me a small favor and hit that like button and subscribe. It genuinely helps this channel grow, and it means we get to keep making journeys like this one together. Are you ready? Brace yourself. Let's begin. You think you know how big the Earth is. You have seen the photographs taken from orbit. You have watched the curved blue horizon in footage shot from the International Space Station. You might have even flown across an ocean and felt, somewhere around the 6th or 7th hour of staring out that tiny oval window, a creeping sense that this planet is genuinely enormous. And by every standard your body and brain evolved to process, you are right. Earth is staggeringly large compared to a human being. But that feeling, that intuitive sense of planetary enormity is the first thing we need to dismantle. Because once you start measuring Earth against the objects that surround it in space, something deeply uncomfortable happens. The planet you stand on, the world that contains every city, every ocean, every mountain range, every war, and every civilization that has ever existed, begins to shrink, and it never stops shrinking. Start with what you can touch. The circumference of the Earth at the equator measures approximately 24,900 miles. That is a real, verified, measured number. You can look it up. You can confirm it with GPS satellites and geodetic surveys. But real numbers and comprehensible numbers are not the same thing, so let us make it physical. If you climbed into a commercial airliner flying at a typical cruising speed of around 550 miles per hour and never landed, never stopped for fuel, never circled around weather systems or waited for clearance, it would take you just over 45 hours to circle the planet. Nearly 2 full days of continuous, non-stop flight just to return to where you started. If you attempted the same trip in a car doing 70 miles per hour on an impossibly straight highway that wrapped around the equator, the drive would take roughly 14.5 days. 2 full weeks of driving without rest, without sleep, without stopping for gas, just to trace the outline of the planet you were born on. That is Earth at human speed. It feels enormous because for a species that spent most of its evolutionary history walking at 3 miles per hour across African grasslands, it genuinely is enormous. Your legs were never designed for this planet's full circumference. Your intuition was calibrated for river crossings and seasonal migrations, not for continental distances. When early humans walked out of Africa roughly 70,000 years ago, the journey to the southern tip of South America took approximately 10,000 years of gradual generational migration. 10,000 years to cross what was, from the planet's perspective, a fraction of its surface. Earth was built on a scale that dwarfed every biological system that ever evolved on it, and human beings were no exception. Now go vertical. The deepest point in Earth's oceans is the Challenger Deep in the Mariana Trench, located in the western Pacific Ocean. It plunges to approximately 36,000 feet beneath the surface. That is nearly 7 miles straight down. At those depths, the water pressure exceeds 16,000 pounds per square inch, roughly 1,000 times the atmospheric pressure you feel standing at sea level. The temperature hovers just a few degrees above freezing. Sunlight vanishes completely within the first 1,000 feet. Below that threshold, the ocean exists in total, permanent darkness. Fewer than 30 people in all of human history have ever reached the bottom. Each descent required custom-built submersibles with titanium pressure hulls designed to withstand forces that would crush a nuclear submarine like an aluminum can. It sounds like a journey to another world. And in terms of the sensory experience, the pressure, the darkness, the cold, it might as well be. But here is the number that reframes everything. Earth's diameter is roughly 7,918 miles. The Mariana Trench, the single deepest scar on our planet's surface, represents a scratch less than 7 miles deep on a sphere nearly 8,000 miles across. To put this in tactile terms, if you shrank Earth to the size of a standard basketball, the Mariana Trench would not even be detectable by a human fingertip. You could run your hand across the entire surface of that basketball, and the deepest point in the ocean, the most extreme depth our planet possesses, would feel like nothing. Perfectly smooth, imperceptible. The feature that required custom engineering and decades of technological development for humans to reach is, at planetary scale, a rounding error. It might as well not exist. This is the first lesson in cosmic scaling. Things you believe are immense often turn out to be immeasurably small when you simply zoom out by one level. The Mariana Trench overwhelms human engineering. It challenges human survival. It represents a genuine frontier of exploration. And yet, to the planet itself, it is a scratch too shallow to notice. Keep this pattern in mind. It is going to repeat at every scale we encounter from this point forward. And each time it repeats, the thing that just felt enormous will be the thing that becomes invisible. We have not even left the planet yet. Earth orbits the Sun at an average distance of approximately 93 million miles. Astronomers call this distance 1 astronomical unit, or AU, and it serves as the baseline measurement for everything else in the solar system. 93 million miles. Let us try to make that number mean something to a human body. At the speed of a commercial airplane, that journey would take over 19 years of continuous flight. 19 years in the air without landing. A child born the day you took off would be entering adulthood by the time you arrived. At the speed of a bullet fired from a high-powered rifle, roughly 1,700 miles per hour, you would still need more than 6 years to reach the Sun. 6 years at bullet speed. And even light, the fastest phenomenon in the known universe, travelling at roughly 186,000 miles per second, requires 8 minutes and 20 seconds to cross from the Sun's surface to your eyes. Think about what that means in practical terms. When you look up at the Sun, you are not seeing it as it exists right now. You are seeing it as it was over 8 minutes ago. If the Sun were to catastrophically vanish this instant, you would not know for 8 minutes and 20 seconds. You would still feel the warmth on your skin. You would still see the light in the sky. You would continue living in complete ignorance of the event for the time it takes to brew a pot of coffee and pour a cup. That is how far away we are from our own star. But the distance is only half the story. The Sun itself is a monstrosity of scale that makes Earth look like a fleck of dust drifting through a furnace. The Sun's diameter measures approximately 864,000 miles. To put that into direct comparison, the Sun is roughly 109 times wider than Earth. You could line up 109 Earths side by side, and they would just barely stretch across the Sun's face from edge to edge. Its volume is even more devastating. Approximately 1.3 million Earths could fit inside the Sun. Not beside it, not next to it, inside it. Every continent, every ocean, every mountain range and desert and glacier and city replicated 1.3 million times over, and the Sun would swallow all of them with room to spare. The object you see rising every morning is not a gentle lamp in the sky. It is a sphere of superheated plasma so massive that it contains 99.86% of all the mass in the entire solar system. Everything else, every planet, every moon, every asteroid, every comet, every grain of dust drifting between the orbits, makes up the remaining 0.14%. Jupiter, the largest planet in our system, which could itself contain over 1,300 Earths inside its volume, is a gravitational footnote compared to the Sun. Earth does not even register as a footnote. It is a cosmic speck orbiting a thermonuclear engine that converts approximately 4 million tons of its own mass into pure energy every single second through nuclear fusion. Let that number settle. 4 million tons of matter per second. Not per year, not per day, per second. That is the mass equivalent of roughly 22,000 fully grown blue whales annihilated every tick of the clock, their matter converted entirely into electromagnetic radiation and neutrinos. And the Sun has been sustaining this output continuously for approximately 4.5 billion years. It will continue for roughly another 5 billion before it exhausts its hydrogen fuel supply and begins its transformation into a red giant star, eventually shedding its outer layers and collapsing into a white dwarf remnant. In cosmic terms, our star is middle-aged, stable, and spectacularly ordinary. It ranks among the most common category of stars in the galaxy, classified as a G-type main sequence star. It is not particularly bright, it is not particularly massive, it is not particularly old, and yet its scale makes every structure humanity has ever built, every distance humanity has ever travelled, every measurement humanity has ever taken on the surface of this planet. Feel like a child's drawing taped to the wall of a cathedral. Here is where the emptiness begins. Earth sits 93 million miles from the Sun. Mars orbits farther out at approximately 142 million miles. Jupiter, the first and largest of the gas giants, circles at roughly 484 million miles. Saturn, famous for its ring system, drifts at 886 million miles. Uranus at approximately 1.8 billion miles. And Neptune, the outermost recognized major planet, orbits at a staggering 2.8 billion miles from the Sun. That is the span of our solar system when measured by the major planetary orbits. Nearly 3 billion miles from center to edge, a beam of light leaving the Sun takes over 4 hours to reach Neptune. A radio signal sent from mission control on Earth to a spacecraft operating near Neptune, traveling at the absolute speed limit of the universe, requires approximately 4 hours to arrive. If a spacecraft near Neptune encountered an emergency and radioed home for instructions, the operators in Houston would not receive the distress call for 4 hours. Their response would take another 4 hours to travel back, 8 hours of round-trip communication delay at the fastest speed physics allows. For all practical purposes, a spacecraft near Neptune operates alone. This isolation is not theoretical. It has been experienced by every deep space mission humanity has ever flown. When NASA's New Horizons spacecraft flew past Pluto in July of 2015, its closest approach happened entirely on autopilot. Mission controllers had uploaded the flyby commands hours in advance because the one-way signal travel time from Earth to Pluto exceeded 4.5 hours. There was no possibility of real-time guidance, no possibility of corrective commands during the encounter. The spacecraft executed its observations alone, stored the data on board, and then spent over 15 months slowly transmitting the results back to Earth at a trickle of roughly 1 to 2 kilobits per second. The entire data set from a flyby that lasted hours took more than a year to download across the solar system, and Pluto is close compared to the outer boundary of the Sun's domain. Voyager 1, now more than 15 billion miles from Earth, communicates with a radio transmitter that operates at roughly 22 watts, about the power of a refrigerator light bulb. Its signal, spreading outward in all directions as it crosses the solar system, is so faint by the time it reaches NASA's Deep Space Network antennas on Earth that the received power measures roughly 0.000000000000001 watts. That is roughly 10 billion times weaker than the power needed to operate a standard digital wristwatch. Engineers must use cryogenically cooled receivers and hours of signal averaging just to extract intelligible data from the noise. And Voyager 1 has not even left the Sun's gravitational sphere of influence. It is still, by any meaningful definition, inside our solar system. This is what emptiness means in real engineering terms. Not abstract distance on a chart, but the concrete, measurable degradation of every signal, every communication, every link between a human-made object and the civilization that built it, stretched to the breaking point across voids that exist between objects within our own tiny stellar neighbourhood. But even Neptune does not mark the true boundary of our solar system. The Sun's gravitational influence extends enormously beyond the last planet. The Kuiper Belt, a ring of icy bodies beyond Neptune's orbit, stretches from roughly 30 to 50 astronomical units from the Sun. Beyond that lies the scattered disk, and farther still, the hypothesized Oort cloud, a vast, spherical shell of icy objects estimated to extend from roughly 2,000 to as far as 100,000 astronomical units from the Sun. 100,000 astronomical units translates to approximately 1.6 light-years. The full gravitational domain of our single, unremarkable middle-aged star stretches across a sphere potentially 2 to 3 light-years in diameter. 1 light-year equals approximately 5.88 trillion miles. The Sun's sphere of gravitational influence extends trillions upon trillions of miles into surrounding space, claiming a volume of cosmic territory so enormous that the planets, all 8 of them, occupy an almost invisible sliver at the very centre. Now consider Voyager 1. Launched by NASA on September 5, 1977, aboard a Titan IIIe Centaur rocket, Voyager 1 is the farthest human-made object from Earth. After nearly 5 decades of continuous travel at approximately 38,000 miles per hour, it has covered roughly 15 billion miles from the Sun. 15 billion miles in 47 years. That sounds like a monumental achievement of human engineering, and in many ways, it is. Voyager 1 has crossed the heliopause, the boundary where the solar wind gives way to the interstellar medium, making it the first human-made object to enter interstellar space. But here is the reality that diffuses any sense of triumph. Despite travelling for nearly half a century at 38,000 miles per hour, Voyager 1 remains well within the Sun's extended gravitational sphere. It has not escaped our star's neighbourhood. It has barely entered the front yard. At its current velocity, Voyager 1 would require approximately 73,000 years to cover the distance to Proxima Centauri, the nearest star to our Sun, if it were heading in that direction, which it is not. 73,000 years. That is roughly 9 times longer than all of recorded human civilization. The fastest object our species has ever launched into space cannot reach the next star over in any time frame relevant to the survival of nations, languages, or even species. This is the emptiness that defines our solar system. Not the planets, not the moons, not the rocky debris in the asteroid belt or the icy fragments in the Kuiper Belt. The defining physical characteristic of our solar system is the absolutely staggering volume of empty space between objects. Space that contains functionally nothing. No air, no sound, no resistance, no landmarks, no rest stops. Just vacuum extending in every direction for billions upon billions of miles, punctuated by occasional lumps of rock, gas, or ice so small relative to the distances separating them that locating them requires precise mathematical coordinates rather than any form of visual scanning. Let us make this visceral with a scale model. Imagine shrinking the Sun down to the size of a large grapefruit, roughly 8 inches across. At that scale, Earth would be reduced to the size of a small pebble, less than an inch across, sitting about 75 feet from the doorway. Mars would be a slightly smaller pebble at approximately 115 feet. Jupiter, the giant of our planetary family, would be a ball roughly 6 inches in diameter, hovering at about 390 feet from the door. Saturn would sit at roughly 717 feet. And Neptune, the most distant major planet, would be a ball slightly smaller than Jupiter, sitting nearly half a mile away from that front door. Half a mile. And the Sun in this model is an object you could hold in one hand. The entire solar system, compressed to this human-friendly scale, would span a modest small town, and nearly every square foot of that town would be completely empty. No buildings, no trees, no objects of any kind. Just empty ground between a door and a handful of scattered balls stretching toward the horizon. But it is the next step in this model that reveals the true nature of the emptiness. At this same scale, where the Sun is a door and Earth is a pebble 75 feet away, the nearest neighbouring star system, Proxima Centauri, would be located approximately 4,000 miles away. Imagine standing at your front door in New York City. Proxima Centauri, the closest star to our Sun, would be another front door sitting somewhere in the middle of the Pacific Ocean, halfway to Japan. 4,000 miles of empty, featureless terrain between one star and its nearest neighbour. That is the gap between suns in our region of the galaxy. The space between stars is not simply larger than the space between planets. It belongs to an entirely different category of distance. It dwarfs everything within the solar system by factors so extreme that direct comparison feels almost meaningless, like comparing the width of a human hair to the distance across the Atlantic. And that space is not merely empty. It is hostile in ways that extend beyond simple vacuum. The interstellar medium, the material that fills the space between stars in our region of the Milky Way, contains on average roughly 1 atom per cubic centimetre. That is incomprehensibly sparse compared to any environment on Earth. The air in your living room contains approximately 25 billion molecules per cubic centimetre. But even at this extraordinarily low density, the interstellar medium is not nothing. It contains stray hydrogen atoms, helium atoms, trace amounts of heavier elements, microscopic dust grains, and a bath of high-energy cosmic ray particles accelerated to near light speed by distant supernovae and other violent astrophysical processes. Magnetic fields thread through this medium, weak but measurable, stretching across light years of space. For a spacecraft travelling at low speeds, like Voyager 1, this material is irrelevant. The density is far too low to produce any measurable drag or damage. But for a spacecraft travelling at any significant fraction of the speed of light, the interstellar medium transforms from an invisible background into a serious physical hazard. At 10% of light speed, approximately 67 million miles per hour, each individual hydrogen atom encountered by the spacecraft would strike the hull with the energy of a high-energy particle accelerator collision. Over the course of a 4-light-year journey to Proxima Centauri, the cumulative bombardment from trillions upon trillions of these impacts would deliver a punishing dose of radiation to the spacecraft's surface, erode shielding materials, and potentially degrade sensitive instruments beyond functionality. The interstellar medium also contains dust grains, each one microscopic by earthly standards, but travelling at a relative velocity of 10% of light speed, each grain impact would carry the kinetic energy of a small explosive charge. The void between stars is not a passive emptiness waiting to be crossed. It is a thin, invisible gauntlet that grows more dangerous the faster you attempt to cross it. Even at the smallest interstellar scales, even within the relatively dense disk of our own galaxy, the space between stars punishes speed and rewards patience that no biological organism possesses. And yet, these interstellar voids are just the gaps between individual houses in a city of 400 billion houses. All of this, the planets, the Sun, the Voyager spacecraft, the 15 billion miles of distance travelled over nearly 5 decades, exists inside a single galaxy, the Milky Way, a structure so vast that the entire solar system, with all of its planets and moons and comets and billions of miles of empty space, would not register as a single visible dot on a photograph taken from outside it. The numbers that describe the Milky Way are so far beyond anything we have encountered so far that they deserve their own full treatment, and they will get it. But first, understand this. Everything measured so far, every distance that made your intuition flinch, every comparison that forced you to recalibrate your sense of what qualifies as large, describes a region of space so tiny within our galaxy that it is, for all practical purposes, invisible. Here is where everything we have measured collapses into insignificance. If you placed a single grain of rice at the 50-yard line of an American football field and declared that grain to be the entire solar system, the football field would not even begin to represent the Milky Way. At that scale, our galaxy would extend far beyond the stadium, beyond the parking lot, beyond the surrounding neighbourhoods, beyond the city limits. The grain of rice sitting at midfield would be invisible to anyone sitting in the stands. You could walk down to the 50-yard line, drop to your knees, and search the turf with a magnifying glass, and you would struggle to find the grain that represents everything you have ever known. Every signal humanity has ever broadcast into space has travelled outward at the speed of light for roughly 120 years since the first radio transmissions in the early 20th century. That means our electromagnetic footprint, the sum total of every radio wave, every television signal, every radar pulse, every intentional and unintentional transmission our species has ever produced, extends approximately 120 light-years from Earth in all directions. 120 light-years sounds enormous, but the Milky Way is 100,000 light-years across. Our loudest shout into the cosmos has covered approximately 0.1% of our own galaxy's diameter. If the Milky Way were a dining room table, our entire radiosphere would be a penny lying on the surface. To any observer on the other side of the galaxy, to any civilization watching from 50,000 light-years away, humanity does not exist. Our signals have not arrived. They will not arrive for tens of thousands of years, and even when they do, they will be so faint, so diluted by the inverse square law governing electromagnetic radiation, that detecting them would require sensitivity far beyond anything we can currently build. This is not speculation. These are distances measured by space telescopes, confirmed by multiple independent research teams, published in peer-reviewed astrophysical journals, and verified across decades of observation. The European Space Agency's Gaia spacecraft has catalogued the precise positions and motions of nearly 2 billion individual stars in our galaxy. NASA's Hubble and James Webb Space Telescopes have imaged structures at distances that make the entire Milky Way look like a single spark in a bonfire. The measurements are confirmed, the numbers are real, and they are only the starting point of this story, because everything described so far, every measurement, every distance, every comparison that stretched or broke your intuition, describes only our solar system and its position within the galaxy it inhabits. We have not yet turned our attention beyond the Milky Way. We have not yet looked at what lives just outside our galactic borders, a structure so large it makes our entire galaxy look modest by comparison. A structure containing approximately 1 trillion stars spread across a disk more than double the diameter of our own. A structure that is, right now, at this very moment, closing the distance between itself and us. The giant next door has a name, and by every measurable standard available to modern astronomy, it is bigger than the place we call home. So far, we measured the Earth, we measured the Sun, we measured the distances between planets and the emptiness that defines the solar system. Every single one of those measurements felt enormous at human scale, and every single one of them collapsed into insignificance the moment we placed it inside the context of the Milky Way galaxy. The solar system, with all its planets and moons and comets and billions of miles of empty space, registered as an invisible speck within a structure containing hundreds of billions of stars spread across 100,000 light-years of space. That is where we stand. Standing at the edge of local understanding, staring into a galaxy so large that our entire stellar neighbourhood vanishes inside it like a single grain of sand dropped into the ocean. Now we need to go further, because the Milky Way, as incomprehensibly vast as it is, does not exist alone, and what sits next to it makes our galaxy look modest. But before we leave the Milky Way, we need to understand exactly what kind of structure we inhabit. because only by grasping the full scale of our home galaxy can you appreciate just how dramatically the next object dwarfs it. The Milky Way is a barred spiral galaxy. Seen from above, it would resemble a vast pinwheel with curved arms of stars, gas, and dust spiraling outward from a dense central bar of older reddish stars. The disk of visible stars measures approximately 100,000 light-years in diameter. To cross it at the speed of light, the absolute fastest anything can travel in this universe, would take 100,000 years. A beam of light departing from one edge of the Milky Way on the day you were born would not reach the opposite edge until roughly 100,000 years after every trace of human civilization had crumbled to dust and been forgotten. That is the width of the galaxy we live in. 100,000 light-years of stars, gas, dust, dark matter, stellar nurseries, supernovae remnants, neutron stars, black holes, and vast stretches of interstellar vacuum, all bound together by gravity into a single rotating structure. The disk itself is relatively thin compared to its width. At roughly 2,000 light-years thick in the region near our Sun, the Milky Way is shaped more like a dinner plate than a ball, but even 2,000 light-years of thickness represents an immense vertical expanse. Light needs 2 millennia to travel from the top of the galactic disk to the bottom in our neighbourhood. When the Romans were building their first roads across Europe, a photon leaving the upper surface of the Milky Way's disk near our position would only now be arriving at the lower surface. 2,000 years of travel at the fastest speed the universe allows, just across the thin edge of the galaxy. Within this disk, the Milky Way contains between 200 billion and 400 billion individual stars. The exact number remains uncertain because our position inside the galaxy limits our ability to count stars on the far side, where thick clouds of interstellar dust block visible light. Infrared surveys have improved our estimates enormously, but a precise census of every star in the Milky Way remains beyond current capability. What we do know is that the number is staggering. If you attempted to count every star in our galaxy at a pace of 1 star per second, never pausing to eat, sleep, or rest, the task would take you somewhere between 6,300 and 12,700 years. You would need to begin counting before the construction of the Egyptian pyramids, and continue without interruption past the present day and far into the future before you finished. Each of those hundreds of billions of stars is a sun. Some are far larger and more luminous than ours. Blue supergiants like Rigel burn with luminosities exceeding 100,000 times the sun's output. Red hypergiants like UY Scuti have diameters so vast that if placed at the centre of our solar system, their surfaces would extend beyond the orbit of Jupiter. Others are far smaller and dimmer. Red dwarf stars, which make up roughly 70% of all stars in the Milky Way, burn with such feeble luminosity that not a single one is visible to the naked eye from Earth. Despite being the most common type of star in the galaxy, our Sun falls somewhere in the middle of this stellar spectrum. It is brighter than most stars, dimmer than many, larger than some, smaller than others. In a galaxy of hundreds of billions, our star is profoundly average. Our solar system sits approximately 26,000 light-years from the galactic centre. We are not near the core. We are not at the edge. We occupy a position roughly halfway out along the disk, embedded in a minor structure called the Orion Spur, which branches off between 2 of the galaxy's major spiral arms, the Sagittarius Arm and the Perseus Arm. In galactic terms, we live in the suburbs. Not the dense, active downtown core where stars are packed thousands of times more tightly than in our neighbourhood, but not the sparse outer rim where star density thins to almost nothing. We are in a middling region of a middling arm of a galaxy that itself, as we are about to discover, turns out to be middling among its immediate neighbours. The Sun and everything gravitationally bound to it orbits the galactic centre at a speed of approximately 515,000 miles per hour. Despite this tremendous velocity, the sheer scale of the Milky Way means that one complete orbit takes roughly 230 million years. This period is sometimes called a galactic year, and it provides one of the most disorienting perspective shifts available in astronomy. In the 4.5 billion years since the solar system formed, the Sun has completed approximately 19 or 20 full orbits of the galaxy. The last time our star occupied this exact position in the Milky Way, roughly 230 million years ago, the Earth was in the early Triassic period. Dinosaurs were just beginning to appear. The supercontinent Pangaea was still largely intact. No grass existed anywhere on the planet, no flowers, no birds. The world was populated by creatures that would be almost unrecognizable to modern eyes. That is how long a single galactic orbit takes, and the Sun has done it only about 20 times in its entire existence. To understand how invisible our solar system is within this structure, consider one more comparison. If you were standing at the center of the Milky Way and looked outward toward our Sun, locating it would be functionally equivalent to standing in the middle of a completely darkened Manhattan at night and trying to identify one specific firefly hovering somewhere among 400 billion other fireflies scattered across the island. Every firefly is glowing, every firefly is moving, and the one you are looking for is utterly average in brightness, utterly average in size, and located in a section of the island with no distinguishing features whatsoever. You would never find it. Not in a human lifetime. Not in 1,000 human lifetimes. Our Sun, and everything orbiting it, is one faint point of light among hundreds of billions in a galaxy, 100,000 light-years across. This is the full scale of the Milky Way. It is the structure that contains every star you have ever seen in the night sky. Every constellation, every planet visible to the naked eye, every meteor shower, every aurora, all of it occurs within this single galaxy. When you look up on a dark night and see the pale, milky band of light stretching across the sky, you are seeing the combined glow of billions of distant stars in the galactic disk, too far away to be resolved individually, blending into a luminous river of light. That river is your home. It is the largest structure most people will ever contemplate. And it is not the largest thing in our immediate cosmic neighbourhood, not even close. On a clear autumn night in the Northern Hemisphere, if you know where to look, you can find a faint smudge of light in the constellation Andromeda. It appears dim, slightly fuzzy, easily mistaken for a tiny cloud or an imperfection in your vision. Ancient astronomers catalogued it as a nebula, a cloud of glowing gas within our own galaxy. For centuries, that is what scientists believed it was. The idea that this smudge could be anything grander than a local gas cloud did not seriously enter scientific discussion until the early 20th century. And when the truth finally emerged, it shattered every existing model of the universe's size. The story of that discovery deserves to be told properly, because it represents one of the most dramatic single nights in the history of human knowledge. In the early 1920s, the scientific community was locked in what became known as the Great Debate. On one side stood astronomers who believed the Milky Way constituted the entire universe, with the spiral nebulae visible in telescopes being merely clouds of gas within our own galaxy. On the other side stood those who suspected the spiral nebulae were island universes, entire galaxies comparable to our own, located at vast distances beyond the Milky Way's borders. Neither side had definitive evidence. The debate raged in lecture halls and journal pages, unresolved and increasingly contentious. Edwin Hubble settled it. Working with the 100-inch Hooker telescope at Mount Wilson Observatory in Southern California, at the time the largest operational telescope on Earth, Hubble spent months exposing photographic plates aimed at the Andromeda Nebula. The Hooker telescope's unprecedented light-gathering power allowed him to resolve individual stars within the nebula for the first time, separating what had appeared as a diffuse glow into discrete points of light. Among these resolved stars, Hubble identified a Cepheid variable, a type of star whose brightness pulsates in a regular, predictable cycle. The critical insight came from the work of astronomer Henrietta Swan Leavitt, who had established years earlier, through painstaking observations of Cepheids in the Magellanic Clouds, that the pulsation period of a Cepheid is directly and reliably related to its intrinsic luminosity. A Cepheid that pulsates slowly is genuinely brighter than one that pulsates rapidly. This period luminosity relationship gave astronomers a cosmic measuring tool of extraordinary power. By observing the pulsation period of a Cepheid, you could determine its true brightness. By comparing that true brightness to its apparent brightness as seen from Earth, you could calculate its distance using the inverse square law of light. Hubble applied this method to the Cepheid he had found in Andromeda. The pulsation period told him the star's true luminosity. Its faintness as observed from Earth told him it was enormously far away. When he completed the calculation, the result was staggering. The star, and therefore the nebula containing it, was located approximately 900,000 light-years from Earth. A distance later revised upward to approximately 2.5 million light-years as distance measurement techniques improved over subsequent decades. This was far beyond the estimated boundaries of the Milky Way. The Andromeda Nebula was not a gas cloud within our galaxy. It was a galaxy in its own right, a separate island of stars at an almost incomprehensible distance. In a single calculation, derived from a pulsating star on a photographic plate, the known universe expanded from one galaxy to at least two. The great debate was over. The cosmos had just become unimaginably larger than almost anyone had dared to propose. That faint smudge you can see with your naked eye is the Andromeda Galaxy, designated Messier 31 or M31 in astronomical catalogues. It is the most distant object visible to the unaided human eye. And what you are looking at, that gentle, barely perceptible glow, is the combined light of approximately 1 trillion stars. 1 trillion, not billion, trillion. To put that number in direct comparison, the Milky Way contains between 200 billion and 400 billion stars. Andromeda contains roughly 1 trillion. Depending on which estimate you use for our galaxy, Andromeda harbours between 2.5 to 5 times as many stars as the Milky Way. Every star in our galaxy, every sun that powers every planet that harbours every possibility of life within the Milky Way, could be multiplied several times over and still not match the stellar population of the galaxy next door. When you look at that faint smudge in the autumn sky, you are seeing a structure that contains more individual suns than the total number of stars in your home galaxy. That simple act of looking, something any human with functional eyesight can do on a clear night, connects your retina to photons that originated from a system of 1 trillion nuclear furnaces burning across a disk of space more than twice the width of everything you have ever known. Andromeda's disk stretches across approximately 220,000 light-years. The Milky Way's disk spans roughly 100,000 light-years. If you place both galaxies side by side, Andromeda would dwarf our galaxy the way a beach ball dwarfs a tennis ball. More than double the diameter means far more than double the area. The surface area of Andromeda's disk is roughly 4 to 5 times that of the Milky Way's disk. It is not simply a bigger version of our galaxy. It is a categorically larger structure, a galactic giant that makes our home look like a smaller companion rather than an equal neighbour. The structural differences extend beyond raw size. Andromeda is also a spiral galaxy, but its spiral arms are more tightly wound than the Milky Way's, and its central bulge, the dense concentration of older stars surrounding the galactic core, is significantly more prominent. The Milky Way's central bulge is relatively modest and elongated into a bar shape. Andromeda's bulge is rounder and more massive, containing a far larger population of older, redder stars. This structural difference tells astronomers something important about each galaxy's history. The size and shape of a central bulge is influenced by a galaxy's merger history. Larger bulges typically indicate more past collisions with other galaxies. Andromeda's prominent bulge suggests it has consumed more satellite galaxies over its lifetime than the Milky Way has, growing its central regions through repeated gravitational cannibalism across billions of years. Both galaxies harbour supermassive black holes at their centres. In the Milky Way, the central black hole is called Sagittarius A star. It weighs approximately 4 million times the mass of our Sun. 4 million solar masses sounds immense, and it is, but Andromeda's central black hole dwarfs it. Designated M31 star, or sometimes simply the Andromeda black hole, it weighs in at approximately 100 million solar masses. That is roughly 25 times heavier than the Milky Way's central black hole. If Sagittarius A star is a boulder sitting at the center of our galaxy, Andromeda's black hole is a small mountain. This difference in central black hole mass further reflects the difference in each galaxy's accretion history. Larger black holes grow through consuming more material over cosmic time, fed by infalling gas and by mergers with other black holes brought in by absorbed satellite galaxies. Andromeda's significantly larger central black hole tells us that it has had access to, and consumed, far more material than our galaxy's core. The globular cluster populations of each galaxy provide yet another axis of comparison. Globular clusters are ancient, dense, spherical collections of stars that orbit a galaxy's core. They are among the oldest structures in any galaxy, with many dating back to within 1 billion years of the Big Bang. The Milky Way possesses approximately 150 known globular clusters. Andromeda has roughly 450, about 3 times as many. Some estimates push Andromeda's globular cluster count even higher, toward 500 or more, though precise counts are complicated by the difficulty of distinguishing genuine globular clusters from background objects at Andromeda's distance. Regardless of the exact number, Andromeda possesses a substantially richer system of these ancient stellar relics. Each globular cluster contains anywhere from tens of thousands to several million stars, packed into a spherical volume only a few dozen to a few hundred light-years across. The sheer number of globular clusters orbiting Andromeda speaks to the galaxy's larger gravitational sphere of influence and its more extensive history of satellite galaxy absorption. But Andromeda's dominance extends beyond its internal structure. It commands an entire gravitational entourage of smaller galaxies. The 2 most prominent satellite galaxies are M32 and M110, both visible in long-exposure photographs of Andromeda as distinct smaller smudges near the main disk. M32 is a compact elliptical galaxy containing roughly 3 billion stars. Despite its relatively modest size, M32 is scientifically fascinating because it orbits remarkably close to Andromeda's disk and shows unmistakable signs of tidal stripping. Andromeda's immense gravity is actively pulling stars away from M32's outer regions, slowly dismantling it across hundreds of millions of years. Simulations suggest that M32 may once have been a much larger galaxy, perhaps a medium-sized spiral, that has been progressively consumed by Andromeda over billions of years of close orbital interaction, stripped down to its dense core. M110, a dwarf elliptical galaxy, orbits at a somewhat greater distance but also shows evidence of gravitational disturbance from its massive host. Its outer regions appear diffuse and irregular, consistent with tidal interaction stretching its structure. Beyond these 2 prominent companions, Andromeda possesses at least 35 confirmed satellite galaxies and likely harbours more awaiting discovery in deeper surveys. This retinue of satellites mirrors the Milky Way's own collection of dwarf companions, including the large and small Magellanic Clouds visible from the southern hemisphere. But Andromeda's satellite system is both more numerous and includes objects in more advanced stages of tidal disruption. Andromeda is not just a larger galaxy. It is a more active gravitational predator, consuming its smaller neighbours more aggressively than the Milky Way currently consumes its own. The evidence of this ongoing cannibalism is written across the streams of tidally stripped stars and disturbed satellite orbits that surround Andromeda's disk. The total mass of each galaxy provides perhaps the most scientifically meaningful comparison, though it is also the most complicated. Galaxy mass includes not just stars and gas, but the vast invisible halos of dark matter that surround every large galaxy. These dark matter halos extend far beyond the visible disk of stars, sometimes reaching several 100,000 light-years from the galactic center. Dark matter does not emit, absorb, or reflect light, making it invisible to telescopes. Its presence is inferred entirely through gravitational effects on visible matter, the rotation speeds of stars, the orbits of satellite galaxies, and the bending of light from background objects. Current estimates place the Milky Way's total mass, including its dark matter halo, at approximately 1 to 1.5 trillion solar masses. Andromeda's total mass has been the subject of considerable scientific debate. Earlier estimates placed it significantly higher than the Milky Way's mass, at roughly 1.5 to 2 trillion solar masses, reinforcing the image of Andromeda as the dominant galaxy in our local neighbourhood. However, more recent studies, particularly those utilising data from the European Space Agency's Gaia spacecraft, have revised some of these estimates. A 2018 study published in the Astrophysical Journal used the dynamics of satellite galaxies and globular clusters orbiting Andromeda to recalculate its total mass, and arrived at a figure closer to 800 billion. Solar masses, surprisingly lower than earlier estimates and potentially comparable to or even slightly less than the Milky Way's mass. Other studies have produced different results, with mass estimates for Andromeda ranging from 800 billion to nearly 2 trillion solar masses depending on methodology, assumptions about the dark matter halo profile, and the specific tracer objects used to infer the gravitational field. What this means in practical terms is that while Andromeda is unambiguously larger in terms of stellar disk diameter, star count, central black hole mass, and globular cluster population, the question of which galaxy is more massive overall remains an active area of scientific investigation. The Milky Way may be the less visually impressive galaxy, but it is not necessarily the less massive one. The two galaxies may be closer to equal in total mass than decades of popular astronomy suggested. This uncertainty itself is scientifically fascinating. It tells us that measuring the total mass of a galaxy, especially the invisible dark matter component that dominates the mass budget, remains one of the most challenging problems in modern astrophysics. Even for our nearest giant galactic neighbour, a galaxy close enough to see with the unaided eye, we cannot yet agree on how much it weighs. But regardless of where the total mass comparison ultimately settles, the visible differences are dramatic and undeniable. Andromeda's disk is more than twice the diameter of ours. Its star count is 2 to 5 times higher. Its central black hole outweighs ours by a factor of 25. Its globular cluster system is 3 times richer. In every visually measurable category, Andromeda is the larger galaxy. If the Milky Way is a mid-sized city, Andromeda is a sprawling metropolis. Both are impressive, both are vast. But one of them has more buildings, wider streets, a denser downtown, and a significantly bigger city hall, and both of them belong to the same gravitational neighbourhood. The Milky Way and Andromeda are the two largest members of a collection of galaxies called the Local Group. This gravitational family contains more than 80 individual galaxies, though the vast majority are small dwarf galaxies containing only a few billion stars or fewer. The Local Group spans roughly 10 million light-years across, with the Milky Way and Andromeda acting as the two dominant gravitational anchors around which everything else orbits. The third largest member, the Triangulum Galaxy, or M33, contains approximately 40 billion stars and sits roughly 3 million light-years from us, relatively close to Andromeda and possibly gravitationally bound to it as a satellite. The Local Group is not a dense cluster. It is a loose association of galaxies bound together by mutual gravitational attraction, with most of its volume consisting of empty intergalactic space. The smaller dwarf galaxies orbit either the Milky Way or Andromeda, much as moons orbit planets. The Milky Way has approximately 50 known satellite galaxies, including the large and small Magellanic Clouds visible from the southern hemisphere. Andromeda has a comparable or slightly larger retinue of satellite dwarfs. These smaller galaxies are slowly being drawn inward by their host galaxy's gravity, and many of them will eventually be torn apart and absorbed, their stars scattered into the halo of whichever giant galaxy claimed them. Within this Local Group, the Milky Way and Andromeda dominate everything. Together, they account for the overwhelming majority of the group's total mass and stellar population. They are the gravitational kings of this particular cosmic neighbourhood, and every smaller galaxy within 10 million light-years exists under their combined influence. But these two kings are not sitting still. They are not maintaining a polite distance from one another across a quiet cosmic suburb. The Milky Way and Andromeda are separated by approximately 2.5 million light-years of intergalactic space. That distance is enormous by any human standard. It represents a gulf so vast that light itself, travelling at 186,000 miles per second, requires 2.5 million years to cross it. The photons arriving at your eyes from Andromeda tonight left that galaxy before the genus Homo existed on Earth. And across that entire immense distance, something is happening. Something slow, gravitational and inevitable. Andromeda is not drifting randomly through space relative to us. It is not receding into the distance like most distant galaxies carried apart by cosmic expansion. Andromeda is approaching. The blue shift of its light, first measured in the early 20th century and confirmed with increasing precision ever since, tells us that the distance between our galaxy and Andromeda is shrinking. The gap is closing at approximately 110 kilometers per second, roughly 250,000 miles per hour. Two galaxies, each containing hundreds of billions to a trillion stars, separated by 2.5 million light-years of functionally empty space, are drawing toward each other under the force of mutual gravitational attraction. The implications of this approach, the timeline, the geometry, the physics of what happens when they meet, and the fierce ongoing scientific debate about the precise nature of that meeting, I form the core of the next chapter of this story. Because the distance between the Milky Way and Andromeda is not merely a number, it is a physical space so vast that it breaks every intuitive framework the human brain has for understanding separation. It is a gap so extreme that translating it into any unit of measurement a person can visualize produces results that stop functioning as meaningful descriptions of distance and start functioning as evidence that the universe was not designed for human comprehension. Every analogy fails, every comparison collapses under the weight of the actual figures. And what is moving across that distance, what is slowly, gravitationally, inexorably closing that gap at 250,000 miles every single hour, is the single largest object you will ever see with your own eyes. What comes next is the distance itself, and it is where the human mind finally reaches its limit, 2.5 million light-years. That is the distance between the Milky Way and the Andromeda Galaxy. It is the number that has been floating in the background of this entire story, waiting for the moment when we finally stop and stare directly at it. We have spent this entire journey building toward this distance. We measured the Earth and found it enormous at human scale, but invisible at planetary scale. We measured the solar system and found it vast by any terrestrial standard, but invisible within the Milky Way. We measured the Milky Way and found it incomprehensibly large, containing hundreds of billions of stars across 100,000 light-years of space. And then we discovered that the galaxy next door, Andromeda, is more than twice the diameter of our home, contains up to 1 trillion stars, and possesses a central black hole 25 times more massive than ours. Each step on this journey has demolished the sense of scale established by the previous step. Each level of cosmic organization has made the last one disappear. Now we confront the gap between them, and this is where the numbers stop behaving like numbers. This is where the human brain, which evolved to track the distance between a predator and a watering hole, reaches a wall it cannot climb. Let us start with the raw figure and try, honestly and methodically, to make it mean something. 1 light-year is the distance that light travels in 1 year, moving at approximately 186,000 miles per second. In more familiar terms, 1 light-year equals roughly 5.88 trillion miles. That is 5,880,000,000,000 miles. Written out in full, that number is 5, followed by 12 digits. A single light year is already so far beyond anything a human being has ever physically traversed that it functions more as a mathematical concept than a practical distance. No human has travelled even 1% of 1% of 1 light-year from Earth. The farthest any human being has ever been from this planet is the distance to the Moon, approximately 240,000 miles during the Apollo missions. 1 light-year is roughly 24 million times farther than the Moon. Every crewed space mission in human history, every walk on the lunar surface, every orbit of the Earth, every spacewalk conducted from the International Space Station, all of it combined does not begin to approach 1 light-year of distance. Now multiply that figure by 2.5 million. The distance to the Andromeda Galaxy is approximately 2.5 million light-years, which translates to roughly 14.7 quadrillion miles. 14.7 quadrillion, that is 14,700,000 billion miles. The number has 15 digits. It is so large that writing it out in standard notation requires you to count zeros the way you might count steps on a long staircase, losing track somewhere in the middle and having to start again. If you attempted to write this distance out in miles using standard 12-point type on sheets of paper, and you stacked those sheets on top of one another, the stack itself would stretch a distance that your brain would refuse to process. 14.7 quadrillion miles is not a distance you can comprehend. It is a distance you can only accept as a verified fact while acknowledging that your nervous system has no mechanism for turning it into an image, a feeling, or an intuition. But let us try anyway. Let us attempt to translate this distance into something physical. Light travels at the fastest speed the universe allows. Nothing with mass can match it. Nothing with mass can even approach it without requiring infinite energy. And yet light, moving at this ultimate cosmic velocity, requires 2.5 million years to cross from Andromeda to the Milky Way. Think about what that travel time contains. 2.5 million years ago, the genus Homo did not exist. Our ancestors were Australopithecus, walking upright across the African savanna with brains roughly 1/3 the size of a modern human's. They had no language, no tools beyond perhaps the occasional found rock, no fire, no shelter beyond what the landscape offered. They lived and died within walking distance of where they were born, aware of nothing beyond the immediate horizon. The light reaching your eyes from Andromeda tonight left that galaxy before any of that. It departed before the evolutionary branching that would eventually produce Homo habilis, the first species in our lineage to systematically craft stone tools. It departed before Homo erectus learned to control fire, before Homo sapiens developed language, before agriculture, before cities, before writing, before mathematics, before telescopes, before the concept of a galaxy even entered human thought. The entire arc of human evolution, every biological and cultural milestone that separates you from a small-brained primate on the African plains, fits inside the travel time of a single beam of light crossing from Andromeda to here. That light was already ancient when the first humans looked up at the night sky and wondered what the stars were. It was already ancient when Galileo pointed his telescope at Jupiter. It was already ancient when Edwin Hubble proved that the smudge in the constellation Andromeda was not a nebula within our galaxy, but a separate galaxy entirely. 2.5 million years of travel at the speed of light, and light is the fastest thing there is. Now, consider what fills that distance. Or more precisely, consider what does not fill it. The intergalactic space between the Milky Way and Andromeda is not perfectly empty. Scientists have detected extremely tenuous distributions of matter in this region. Hot ionized gas, primarily hydrogen and helium, exists in intergalactic space at temperatures reaching hundreds of thousands of degrees. Trace filaments of dark matter thread through the void, remnants of the large-scale cosmic web that connects galaxies across the universe. Occasionally, a stray star ejected from one galaxy or the other drifts through this space, unbound to any galactic structure, moving alone through the darkness at hundreds of thousands of miles per hour with no destination and no companions. But the density of this material is so extraordinarily low that calling it matter is almost generous. The average density of intergalactic space in the region between the Milky Way and Andromeda is roughly 1 atom per cubic meter. 1 atom. In a volume of space the size of a large cardboard box, you would find on average a single hydrogen atom. For comparison, the air you are breathing right now contains approximately 25 quintillion molecules per cubic centimeter. The difference in density between the air in your lungs and the intergalactic medium between here and Andromeda spans a factor of roughly 10 to the 25th power. It is a difference so extreme that intergalactic space qualifies as the most perfect vacuum that naturally exists anywhere in the known universe. Laboratory vacuum chambers on Earth cannot approach this level of emptiness. The most advanced vacuum systems ever built by human engineers still contain millions of molecules per cubic centimeter. Intergalactic space is emptier than anything we can manufacture. Imagine a swimming pool filled with perfectly pure water, and then imagine removing every molecule from that pool except for a single grain of dissolved salt. The pool would still contain more matter per unit volume than the intergalactic void between our galaxy and Andromeda. This is the space that separates us from the nearest giant galaxy. 2.5 million light-years of almost perfect nothingness. No waypoints, no landmarks, no gravitationally significant objects to navigate by, no sources of fuel or energy, no raw materials for construction or repair, no electromagnetic signals strong enough to serve as beacons. Just a flat, featureless, functionally empty gulf stretching for 14.7 quadrillion miles in every direction between two islands of organized matter that are, relative to the distance between them, vanishingly small. And across this void, something is happening. The Andromeda Galaxy is moving toward the Milky Way. This is not theoretical, it is observationally confirmed. The evidence comes from spectroscopic analysis of Andromeda's light. When an object moves toward an observer, the wavelengths of light it emits are compressed, shifting toward the blue end of the spectrum. This phenomenon, known as blue shift, is the approaching object equivalent of a police siren rising in pitch as it drives toward you. Andromeda's light is blue shifted. The galaxy is approaching. This was first measured by astronomer Vesto Slipher in 1912 at Lowell Observatory in Flagstaff, Arizona, making Andromeda one of the first galaxies ever measured to have a significant velocity relative to our own. The measurement has been confirmed and refined continuously in the centuries since. The current best estimate for Andromeda's radial approach velocity is approximately 110 kilometers per second, which translates to roughly 250,000 miles per hour. At that speed, the distance between the two galaxies shrinks by about 110 kilometers every second. Over the course of one Earth year, Andromeda moves approximately 3.5 billion kilometers closer to us, roughly 23 astronomical units, or about 23 times the distance between the Earth and the Sun. Every year, a distance equivalent to nearly the span between the Sun and Uranus is erased from the intergalactic gap. That sounds fast, and in terrestrial terms, it is. 250,000 miles per hour exceeds the speed of any human-made object by a significant margin. It is fast enough to cross the distance between the Earth and the Moon in about 1 hour. But against the scale of intergalactic space, it is glacially slow. At 110 kilometers per second, closing the full 2.5 million light-year distance to Andromeda would require roughly 4 to 5 billion years. That is approximately the same amount of time the Earth has already existed. The journey that Andromeda is making toward us has been underway for billions of years already, and it will continue for billions more. You will never notice it. Your civilization will never notice it. The entire lifespan of human existence on this planet, from the first Homo sapiens to whatever end we eventually meet, will not be long enough to detect any visible change in Andromeda's position in the night sky through naked eye observation. And here is where the science becomes more complicated than the popular narrative typically acknowledges. For decades, the standard description of the Milky Way-Andromeda interaction has been straightforward. The two galaxies are on a collision course. They will collide head-on in approximately 4 to 4.5 billion years. The merger will produce a single, massive elliptical galaxy. This story has appeared in countless documentaries, textbooks, popular science articles, and planetarium shows. It is one of the most widely known facts in public astronomy. But the full picture is more nuanced, and the scientific community's understanding has evolved significantly in the last decade. The radial velocity of Andromeda, the speed at which it approaches us directly, is well measured. 110 kilometers per second, confirmed by multiple independent studies. However, radial velocity tells you only how fast the gap is closing along the direct line between the two galaxies. It does not tell you how Andromeda is moving sideways relative to that line. This sideways component, known as the transverse velocity, is critical for predicting whether the two galaxies will collide head-on, execute a glancing blow, or even pass each other on the first approach before gravity pulls them back together for a later merger. Measuring the transverse velocity of a galaxy 2.5 million light-years away is extraordinarily difficult. The sideways motion translates into an angular shift on the sky that is tiny almost beyond detection. For years, the transverse velocity of Andromeda was essentially unconstrained by observation, and most models simply assumed it was small enough that a head-on collision was the most likely outcome. This changed with the European Space Agency's Gaia spacecraft. Gaia was designed to measure the precise positions and motions of stars with unprecedented accuracy. By tracking the average motion of stars within Andromeda relative to background quasars, researchers were able to produce the first robust measurements of Andromeda's transverse velocity. Studies published in 2019 using Gaia Data Release 2 estimated Andromeda's sideways motion at approximately 57 kilometers per second, with uncertainties that allow values ranging from roughly 40 to 70 kilometers per second. This is not negligible. A significant transverse component means the two galaxies are not approaching each other in a perfectly straight line. They are on a path that includes a significant sideways offset. What does this mean for the interaction? Several things, all of which introduce honest uncertainty into the story. A higher transverse velocity makes a direct head-on collision on the first pass less likely and a glancing encounter more probable. Instead of a single dramatic impact, the galaxies might perform an initial flyby, passing close enough for their dark matter halos and outer stellar populations to interact gravitationally, but without the immediate full merger that earlier models predicted. After the first pass, gravitational friction and the ongoing mutual attraction between the two galaxies would gradually slow their relative motion, pull them back toward each other, and set up a second approach. This second encounter would likely be closer and slower, leading to a more thorough gravitational entanglement. Subsequent passes would follow, each one drawing the galaxies closer together and dissipating more orbital energy, until eventually, over a period potentially spanning several billion years after first close approach, the two systems would coalesce into a single structure. This revised scenario pushes the timeline for a full merger further into the future, from the commonly cited 4 to 4.5 billion years to perhaps 5 billion, 6 billion, or even closer to 10 billion years depending on the precise orbital parameters. Some models suggest the first close encounter could occur in roughly 4.5 billion years, but the final merger might not be complete until 8 to 10 billion years from now. It is essential to state clearly what is and what is not debated in the astrophysics community. What is not debated is that the Milky Way and Andromeda are gravitationally bound to each other and are approaching. The radial blue shift is confirmed. The gravitational attraction is real. Some form of significant interaction will occur. What remains under active investigation is the precise geometry of the encounter. Whether the first pass is a head-on impact or a glancing flyby, the exact timeline for first close approach, the number of orbits or passes before full coalescence, and the final morphology of the merged galaxy. These details depend on measurements that are still being refined, particularly the transverse velocity, the total masses of both galaxies, including their dark matter halos, and the dynamical friction effects that will govern how quickly orbital energy is dissipated. The honest scientific position is this: a collision is very likely. A merger is almost certain over sufficiently long timescales. But the exact choreography of the encounter, the moment-by-moment gravitational dance of 2 trillion star systems approaching each other across 2.5 million light-years, is still being worked out. Anyone who tells you they know exactly when and how it will happen is oversimplifying. The physics is well understood in principle. The initial conditions are still being measured. But let us set aside the debate about timing and geometry and ask a more fundamental question. What does a galactic merger actually look like? Because the popular imagination conjures images of cataclysmic destruction, fireballs, colliding stars, exploding planets, and that image is almost entirely wrong. A galaxy merger is not a collision in any sense that a human would recognize. Stars do not crash into each other. The reason is simple and has everything to do with the emptiness we explored earlier. Stars within galaxies are separated by truly enormous distances relative to their sizes. In the solar neighbourhood, the average distance between neighbouring stars is roughly 4 to 5 light-years. Each star is a few 100,000 to a few million miles in diameter, but the gaps between them span trillions of miles. If you shrank the Sun to the size of a bowling ball and placed it in the centre of a large cathedral, the nearest neighbouring bowling ball representing the nearest star would be located in a completely different cathedral, in a different city, hundreds of miles away. The space between stars is so vast relative to the sizes of the stars themselves that during a galactic merger, the probability of any 2 stars physically impacting each other is vanishingly small. Statistically negligible. You could run the entire merger simulation billions of times, and direct stellar collisions would remain an extraordinary rarity. What does happen, however, is gravitationally dramatic. When 2 galaxies pass through or near each other, the gravitational forces involved are immense and operate across scales of thousands of light-years. These tidal forces do not need to bring individual stars into contact to reshape both galaxies profoundly. They warp orbits, they stretch spiral arms, they fling stars into entirely new trajectories, sending some on long looping paths into intergalactic space and pulling others deep into the merged galactic core. The organized, elegant spiral structures that characterize both the Milky Way and Andromeda would be progressively distorted, twisted, and eventually destroyed. Over hundreds of millions of years following the first close encounter, the spiral arms would dissolve into chaotic streams and shells of stars. The orderly disk structures would puff up into a rounder, less organized shape. Meanwhile, the gas within both galaxies would respond very differently from the stars. Stars, being compact and widely separated, pass through each other's galactic space without interacting directly. Gas clouds, however, are extended and diffuse. When the gas from 2 galaxies meets during a merger, it collides, compresses, and heats up. This compression triggers enormous waves of new star formation. Regions of both galaxies that had been quiescent for billions of years would suddenly ignite with the birth of millions of new stars, lighting up in infrared and ultraviolet radiation. Astronomers observe this phenomenon in real time in other merging galaxy pairs across the universe. Systems like the Andromeda Galaxies, 2 spirals currently colliding roughly 63 million light-years from Earth, show spectacular bursts of star formation in their overlap regions. Exactly as models predict. The Andromeda Galaxies are not unique. NGC 4676, commonly known as the Mice Galaxies, shows 2 spirals caught in an earlier stage of gravitational interaction, their long tidal tails streaming outward like trails of debris from a slow-motion accident, stretching hundreds of thousands of light-years into intergalactic space. The Cartwheel Galaxy, located roughly 500 million light-years away, captures an even rarer and more violent geometry. It is a ring galaxy, formed when a smaller galaxy punched directly through the center of a larger spiral disk at high velocity, sending a shockwave of compressed gas and triggered star formation, radiating outward in an expanding ring, like a ripple spreading across the surface of a cosmic pond. The smaller galaxy passed completely through and is still visible nearby, leaving behind a bullseye structure of new stars that is unlike anything found in our local cosmic neighbourhood. These systems are not simulations or theoretical predictions. They are real galaxies, observed at various stages of gravitational interaction, providing a visual catalogue of what the Milky Way Andromeda encounter will resemble across different phases separated by hundreds of millions of years. Astronomers study these systems as proxies for our own galaxy's future, using their observed properties to calibrate and validate the computer simulations that model the eventual Milky Way Andromeda merger. This starburst phase would be temporary. The violent compression of gas exhausts the available fuel relatively quickly in cosmic terms. Within a few 100 million years, the easily accessible gas would either be converted into new stars, heated to temperatures too high to collapse, or expelled from the merger region entirely by the energy output of the newly formed stars and any active galactic nuclei triggered by gas falling toward the central black holes. After the starburst, star formation would decline sharply, and the merged galaxy would begin to quiet down. The end state, reached perhaps 1 to 2 billion years after the final coalescence, would be a massive elliptical galaxy. No spiral arms, no disk. Just a roughly spherical or slightly elongated blob of stars orbiting a common centre of mass in randomized directions. Astronomers have proposed several names for this future merged galaxy. Milkomeda, Milkdromeda. The names are light-hearted, but the structure they describe would be immense. A combined system containing somewhere between 1.5 and 2 trillion stars, with a total mass potentially exceeding 2 trillion solar masses, dominated by 1 or 2 supermassive black holes at its centre that would themselves eventually merge in a cataclysmic event, producing gravitational waves detectable, in principle, across the observable universe. What about our solar system? If the Sun still exists at the time of the merger, which depends on the timeline, it would be approaching the end of its main sequence life in approximately 5 billion years, and the full merger might not complete until several billion years after that. But if we assume the Sun or its remnant survives through at least the early stages of the interaction, the most likely outcome is not destruction but displacement. The Sun would be unlikely to collide with any other star, for the same reasons that stellar collisions are negligible across the entire merger. However, gravitational perturbation could alter the Sun's orbit significantly. It might be flung outward into the halo of the merged galaxy, orbiting at a much greater distance from the centre than it currently does. It might be pulled inward toward the galactic core. In some simulations, a small percentage of stars are ejected entirely from the merged system, flung into intergalactic space at high velocity, becoming unbound rogue stars drifting through the void with no galactic home. From the perspective of any inhabitants on a planet orbiting a star caught in this merger, the changes would be imperceptible on human timescales. Galactic mergers unfold over hundreds of millions of years. The night sky would change, gradually, across millennia and millions of years. Unfamiliar stars from Andromeda would appear in constellations that slowly distorted beyond recognition. The band of the Milky Way across the sky would warp, brighten in some regions, dim in others, and eventually dissolve into a more uniform glow as the disk structure was destroyed. New nebulae would appear as star formation erupted across compressed gas regions. But none of this would happen fast enough for any individual, or even any civilization persisting for thousands of years, to perceive as sudden change. A galactic merger is an event measured in geological time, not human time. It would be like watching a mountain erode. The process is real, powerful, and transformative, but you would never see it move. This is the reality of the Milky Way Andromeda interaction. Two structures, each containing hundreds of billions to a trillion stars, approaching each other across 2.5 million light-years of near-perfect vacuum at 250,000 miles per hour. The encounter will take billions of years to unfold. The merger will reshape both galaxies beyond recognition. Stars will be scattered, orbits rewritten, spiral structures erased, and a new, larger galaxy will emerge from the gravitational wreckage of two ancient spirals. and not a single star in either galaxy is likely to physically touch another star during the entire process. The distances are too large, the stars are too small, the timescales are too long. And that combination, the interplay of enormous distances, tiny objects, and billion-year timescales, defines not just this merger, but the fundamental character of the universe at galactic scale. Which brings us to the question this entire episode has been building toward. Not what the universe will do on its own schedule, because the universe has no interest in human schedules or human capabilities. The universe operates on timescales that make civilizations look like sparks from a campfire, bright for a moment and then gone. The question is what this scale means for anyone who lives within it. What does 2.5 million light-years mean for a species that builds rockets? What does a trillion-star galaxy mean for a civilization that has not yet reached the nearest star to its own sun? What does intergalactic distance mean for any biological organism, any technological society, any conceivable intelligence that looks up at Andromeda from a small planet in the Milky Way and wonders whether it could ever go there? The distances we have measured in this story are not abstract. They are physical. They are made of space, real space, and crossing them requires real time, real energy, and real technology. The laws of physics that govern how fast matter can travel through space, how much energy is required to accelerate mass, and how long biological organisms can survive are not suggestions. They are constraints, hard constraints. And what comes next will measure those constraints against the distance to Andromeda and discover exactly where the boundary lies between what human ambition can imagine and what the architecture of the universe will actually permit. That boundary is closer than you think, and it is far more absolute than anything we have encountered so far. We have now measured everything. We know the size of the Earth, we know the size of the Sun, we know the distances between planets and the emptiness that fills our solar system. We know the scale of the Milky Way with its hundreds of billions of stars, and the staggering dimensions of the Andromeda Galaxy with its trillion suns stretching across 220,000 light-years of space. We know the distance between our galaxy and Andromeda, 2.5 million light-years, 14.7 quadrillion miles of functionally perfect vacuum. We know that Andromeda is approaching, that a gravitational interaction is coming, and that the merger of these two galaxies will unfold over timescales measured in billions of years. All of these are confirmed, measured, published, verified facts. The numbers are real, the distances are real, the physics is real. Now comes the part of this story that no amount of engineering optimism or technological ambition can soften. Now we ask the question that every measurement in this journey has been quietly building toward. Could we ever cross that distance? Could any civilization, using any technology, governed by any biology, ever travel from the Milky Way to the Andromeda Galaxy within a time frame that means anything to the beings who attempt it? The answer is devastating. And it comes not from pessimism, but from arithmetic. Let us start with what we have actually built. The fastest object humanity has ever sent into deep space on an outbound trajectory is Voyager 1, travelling at approximately 38,000 miles per hour relative to the Sun. At that velocity, Voyager 1 covers roughly 333 million miles per year. That sounds like rapid progress. It is rapid progress by any standard humans have ever applied to transportation. It is faster than any car, any airplane, any bullet, any rocket-propelled vehicle that has ever carried a human being. And it is laughably, catastrophically inadequate for intergalactic distances. At 38,000 miles per hour, travelling continuously without deceleration, without interruption, without encountering any obstacle or gravitational interference, Voyager 1 would require approximately 44 billion years to reach the Andromeda Galaxy. 44 billion years. The current age of the universe, measured from the Big Bang to this moment, is approximately 13.8 billion years. The journey to Andromeda at Voyager speed would take more than 3 times the entire age of the universe. The universe itself has not existed long enough for our fastest spacecraft to complete this trip. If Voyager 1 had been launched at the moment of the Big Bang, travelling through the infant cosmos before galaxies or stars or planets had even formed, it would still not have arrived at Andromeda by now. It would still have roughly 30 billion years of travel remaining. That is the chasm between human engineering and intergalactic distance. It is not a gap that can be closed with incremental improvement. It is a gap that exists at a fundamentally different order of magnitude from anything our species has ever confronted. New Horizons, the spacecraft that flew past Pluto in 2015, achieved a launch velocity of roughly 36,000 miles per hour. It offers no meaningful improvement over Voyager. At New Horizons speeds, the journey to Andromeda would still require tens of billions of years. The difference between 36,000 and 38,000 miles per hour is cosmically irrelevant. Both speeds are so slow relative to the distance involved that choosing between them is like choosing between two different walking paces for a journey from New York to the surface of Mars. What about the Parker Solar Probe? As of recent measurements, it holds the record as the fastest human-made object relative to the Sun, reaching speeds of approximately 430,000 miles per hour during its closest solar approaches. This is more than 11 times faster than Voyager 1. It represents a genuine leap in achievable velocity for human-built hardware, and at that speed, reaching Andromeda would still take approximately 3.9 billion years. 3.9 billion. The Earth is 4.5 billion years old. That means the fastest object humanity has ever constructed would need a travel time roughly equivalent to the entire current age of our planet to reach the galaxy next door. Complex multicellular life has existed on Earth for roughly 600 million years. The entire history of animals, from the Cambrian explosion to this very moment, fits inside a window of time that represents only a fraction of what the Parker Solar Probe would need. Its velocity, which would flatten any material object on Earth on contact, which exceeds the escape velocity of every planet in our solar system, which represents the absolute pinnacle of current human propulsive achievement, buys us almost nothing. It reduces the travel time from absurd to marginally less absurd. The destination remains unreachable by any factor that matters. But these are existing technologies. What about theoretical ones? What about propulsion systems that do not yet exist but are grounded in real physics? What about the concepts discussed in academic papers and engineering workshops, the designs that might, someday, push a spacecraft to a meaningful fraction of the speed of light? The Breakthrough Starshot initiative, announced in 2016, proposed using ground-based laser arrays to accelerate tiny, lightweight probes to approximately 20% of the speed of light. At that velocity, such a probe could reach the nearest star, Proxima Centauri, in roughly 20 years. It is an ambitious concept, and even if the engineering challenges are eventually solved, the technology would be designed for interstellar distances measured in single-digit light-years, not intergalactic distances measured in millions. But let us be generous. Let us assume a civilization far more advanced than ours manages to build a crude spacecraft capable of sustained travel at 10% the speed of light. This is not a minor assumption. 10% of light speed is approximately 67 million miles per hour, nearly 2,000 times faster than Voyager 1. Achieving this velocity with a crude vehicle would require energy outputs and propulsion efficiencies so far beyond current capability that no serious engineering roadmap exists for producing them. But grant the assumption. At 10% of light speed, the journey to Andromeda would take 25 million years. 25 million years. To put that in biological context, 25 million years ago on Earth, the ancestors of modern great apes had not yet diverged from the ancestors of modern Old World monkeys. The Himalayas were still being actively pushed upward by tectonic forces. The entire evolutionary lineage that produced modern humans, from early primates to Homo sapiens, could fit inside this travel time with room to spare. A spacecraft that departed at 10% of light speed when the first crude primates were swinging through Oligocene forests would arrive at Andromeda roughly around now. The passengers who boarded that ship, if biological passengers were even conceivable for such a journey, would need to sustain not just themselves, but an entire functioning society, a closed ecosystem, a stable technological infrastructure, and a coherent mission purpose across a span of time longer than most mammalian species survive on Earth. The average lifespan of a mammalian species, from first appearance to extinction, is roughly 1 to 2 million years. The journey to Andromeda at 10% of light speed would outlast entire evolutionary lineages by a factor of more than 10. Increase the speed. Assume 50% of light speed, an almost incomprehensible velocity that would require harnessing energy sources far exceeding the total current energy output of human civilization. At 50% of light speed, approximately 335 million miles per hour, the journey to Andromeda takes 5 million years. 5 million years ago, the first members of the genus Australopithecus were appearing in Africa. Everything that separates those small-brained, ape-like hominins from you, every tool, every word, every idea, every city, every war, every scientific discovery, occurred in the time it would take a half-light-speed spacecraft to reach Andromeda. And that spacecraft would need to sustain its passengers, or their descendants, or some form of continuous functioning intelligence across that entire span. Push the speed further. 99% of light speed. At this velocity, relativistic effects become significant. Einstein's special theory of relativity predicts that time passes more slowly for objects moving at velocities approaching light speed, a phenomenon called time dilation. For travelers aboard a spacecraft moving at 99% of light speed, the subjective experience of time would be compressed. The universe outside the ship would age faster than the occupants within it. This effect is real, experimentally confirmed with high-precision atomic clocks flown on fast-moving aircraft and satellites. It is not science fiction. It is measured physics. At 99% of light speed, the external journey time, the time that passes for observers back in the Milky Way, would still be approximately 2.5 million years. The universe does not care how fast you travel. 2.5 million light-years of distance still requires a minimum of 2.5 million years for light or anything approaching light speed to cross, as measured from the stationary frame. But inside the ship, time dilation would compress the subjective experience. Depending on the acceleration profile, the onboard elapsed time could be significantly less than the external time. For a ship that could sustain a constant acceleration of 1g, approximately 9.8 meters per second squared, which would conveniently provide Earth-like artificial gravity for the passengers, the subjective journey time to Andromeda would be reduced to roughly 28 years of experience time. 28 years. That sounds almost manageable. A crew could board in young adulthood and arrive in late middle age. But this scenario conceals problems so severe that they effectively disqualify it from serious consideration as a practical possibility. First, maintaining 1g of constant acceleration for the duration of a 2.5 million light-year journey would require an energy expenditure so enormous that no known or theorized fuel source could provide. The energy required to accelerate a spacecraft of any meaningful mass to 99% of light speed, sustain that acceleration, and then decelerate at the destination exceeds the total energy output of the Sun over significant fractions of its lifetime. We are not talking about difficult engineering. We are talking about energy requirements that would consume stellar-scale power sources. Second, the travelers who arrived at Andromeda after 28 subjective years would step out of their spacecraft into a universe that had aged by 2.5 million years. Every person they knew, every civilization they left behind, every record of their departure would be gone. Not dead for a few generations, gone for 2.5 million years. The Milky Way they left behind would be unrecognizable. Stars would have been born and died. Stellar populations would have shifted. The very position of their home star within the galaxy would have changed. They would arrive as visitors from a past so distant that nothing from their era would remain. Even if the physics of the journey were solved, the travelers would be permanently severed from everything and everyone that existed at the time they departed. This is not exile, it is erasure. But the erasure would extend in both directions. Not only would the Milky Way they left behind have aged beyond recognition, but the Andromeda they aimed for would no longer exist in the form they studied before departure. The galaxy whose maps they carried, whose star charts they memorized, whose spiral arm configurations shaped their approach trajectory, would have undergone 2.5 million years of stellar evolution during their journey. Massive blue stars that burned prominently in their pre-departure observations would have exhausted their fuel and exploded as supernovae, leaving behind neutron stars or black holes where bright landmarks once shone. Millions of new stars would have formed in regions that were nothing but cold gas clouds when the mission was planned. The spiral arms would have rotated into different positions around Andromeda's center. Individual star systems that served as navigational targets would have shifted their locations by measurable amounts due to their own orbital motion within the galaxy. The travelers would arrive at a destination that had aged beyond the recognition of their instruments and their maps. They would carry charts of a galaxy that no longer existed in that configuration, aiming for systems that had moved, navigating by stellar landmarks that had changed or vanished entirely. The journey would deliver them not to the Andromeda they intended to visit, but to its distant descendant. And all of this assumes a level of technology so far beyond anything humanity currently possesses that discussing it in practical terms borders on fantasy. We have not sent a crewed mission beyond the moon. We have not sustained a human being in space for longer than approximately 437 consecutive days, the record set by Valery Polyakov aboard the Mir space station. We have no experience maintaining closed-loop life support systems for more than a few years. We have no propulsion system capable of accelerating a crewed vehicle to even 1% of light speed, let alone 99%. The gap between where human spaceflight technology actually stands and where it would need to stand to attempt an intergalactic crossing is not a gap measured in decades or centuries of progress. It is a gap measured in orders of magnitude so large that the word progress loses its meaning. Generation ships, a concept popular in science fiction, propose a partial workaround. Instead of requiring individual humans to survive the entire journey, a generation ship would carry a self-sustaining population that reproduces across millennia or millions of years, with descendants eventually arriving at the destination. The original passengers accept that they will never see the destination. Their role is to begin the journey and maintain the vessel long enough for future generations to continue it. The concept has a romantic appeal. It reframes the journey from an individual endurance test to a collective civilizational project spanning evolutionary timescales. But the practical challenges are almost indistinguishable from impossibility when applied to the distance to Andromeda. At 10% of light speed, the most optimistically fast generation ship would need to sustain a functioning population for 25 million years. Consider what that requires. A closed ecosystem capable of recycling all water, air, and nutrients without any external resupply for 25 million years. A social structure stable enough to maintain collective purpose across roughly 1 million human generations. A technological infrastructure capable of self-repair and adaptation over timescales longer than most species persist on Earth. Materials that resist degradation across millions of years of continuous use in the harsh radiation environment of intergalactic space. Every single component of the ship, from hull plating to air filtration to food production to genetic diversity management, would need to function without catastrophic failure for a duration that exceeds the entire history of the genus Homo by a factor of more than 3. If every human being who has ever lived on Earth, estimated at roughly 110 billion individuals across the 300,000-year history of Homo sapiens, were to participate in a relay race, where each person ran one leg and passed a baton to the next, the relay would cover a span of time roughly equal to 300,000 years. The journey to Andromeda at 10% of light speed would require that relay to be repeated 83 times over. 83 complete cycles of the entire history of our species back to back, without interruption, without failure, without loss of purpose. No material we have ever manufactured would survive that duration. No social structure we have ever built has persisted for more than a few thousand years, and most collapse within centuries. No ecosystem we have ever observed, natural or artificial, has operated as a closed loop without external energy and material inputs for more than brief experimental periods. The generation ship concept, applied to intergalactic distances, is not a difficult engineering problem. It is a category error. It applies tools designed for interstellar distances, where journeys might be measured in decades or centuries, to intergalactic distances where journeys are measured in millions of years. The two problems are not on the same spectrum. They are separated by the same kind of qualitative gap that separates swimming across a river from swimming across an ocean. And this leads to the hardest realization in this entire story. The distance to Andromeda is not merely a large number, it is a physical boundary. Not a wall in the literal sense, not a barrier made of matter or energy, but something more fundamental. A boundary imposed by the geometry of space, the speed of light, the energy requirements of acceleration, and the biological limitations of every known form of life. Within the framework of known physics, the intergalactic void between the Milky Way and Andromeda constitutes a permanent separation for any biological civilization confined to sub-light speed travel. Permanent. Not temporarily beyond reach, not awaiting a future technological breakthrough, permanently inaccessible within any time frame that a biological species, a culture, a continuous line of technological development could realistically sustain. This is not a statement about human ambition or human intelligence. It is a statement about the architecture of the universe. The cosmos built its structures on scales that do not accommodate biological travel between galaxies. The same laws of physics that allow stars to form, planets to coalesce, and life to evolve also impose speed limits, energy constraints, and distance scales that confine any civilization born within a galaxy to that galaxy. The Milky Way is not a launching pad for intergalactic exploration. It is, for all practical purposes within known physics, the entire accessible universe for any species that calls it home. Even within the Milky Way, the distances are staggering. The nearest star is 4.25 light-years away. The galaxy spans 100,000 light-years. A civilization that mastered interstellar travel at 10% of light speed could explore a significant fraction of the Milky Way over millions of years, seeding itself across thousands of star systems, building a galactic network of extraordinary scope. But the jump from intragalactic to intergalactic travel is not a step. It is a chasm. The distance to Andromeda is 25 times the diameter of the entire Milky Way. It requires crossing 2.5 million light-years of empty space, with no stars to visit along the way, no resources to harvest, no gravitational assists to exploit, no intermediate destinations to provide rest or resupply. It is the longest, emptiest, most resource-barren crossing conceivable, and it must be completed in a single, unbroken journey spanning millions of years. If an ant stood on a globe in the middle of a vast, featureless desert, and you told it that another globe existed somewhere in the desert, several miles away with nothing but flat sand between them, the ant could comprehend the direction. It could even begin walking. But the distance between the globe it stands on and the globe it cannot see would exceed every capability the ant possesses by so many orders of magnitude that the journey would be meaningless. The ant would die before covering a fraction of a percent of the distance. Its descendants, if they could somehow continue the journey, would face the same limitation. The desert is simply too wide for the organism attempting to cross it, not because the ant is flawed, not because the desert is hostile, but because the scale of one is incompatible with the capabilities of the other. That is the relationship between human civilization and the distance to Andromeda. The scale of the universe is incompatible with the biological, energetic, and temporal capabilities of any known form of life. This is not a failure of imagination. It is a measured, quantified, verified physical constraint. And yet, stand outside on a clear autumn night, look toward the constellation Andromeda, find the faint smudge of light that ancient astronomers mistook for a local cloud of gas. Hold your gaze there. What you are looking at is the combined glow of 1 trillion stars burning across a disk of space 220,000 light-years wide, located 2.5 million light-years from your eyes. The light entering your retina tonight left that galaxy before your species existed. It has been travelling through the intergalactic void for longer than the entire evolutionary history of human intelligence. And now it is ending its journey on the surface of your eye, converted into an electrical signal by cells in your retina, transmitted through your optic nerve, and processed by a brain that weighs 3 pounds and runs on roughly 20 watts of power. You cannot go there. No technology you will likely ever build can take you there. The distance is too vast, the time too long, the energy too great, the biology too fragile. Andromeda will remain forever beyond physical reach for any human being, any human civilization, and quite possibly any biological organism that will ever exist in the Milky Way. But you can see it, you can measure it, you can calculate its mass, count its stars, map its spiral arms, identify its central black hole, determine its velocity, predict its trajectory, and model its eventual gravitational interaction with your home galaxy. You can do all of this from the surface of a single planet, orbiting a single average star in the quiet suburbs of a galaxy that is, by measurable standards, the smaller sibling of the pair. The Milky Way contains between 200 billion and 400 billion stars. Current estimates suggest it harbours somewhere between 100 billion and 300 billion planets, a significant fraction of them orbiting within the habitable zones of their host stars, where conditions might permit liquid water to exist on their surfaces. This single galaxy, the one we are confined to, provides a cosmic territory so immense that a civilization travelling at 10% of light speed would need 1 million years to cross it from edge to edge. No species that has ever existed on Earth has persisted for 1 million continuous years of technological civilization. The Milky Way alone offers more space, more stars, more planets, more potential destinations, more unanswered questions, and more undiscovered worlds than any single civilization could exhaust in the entire remaining lifespan of the Sun. We are not locked in a prison cell. We are confined to an arena of almost limitless possibility that we have barely begun to explore. Andromeda, the giant next door, doubles that territory, but it doubles it across a gap that physics will not let biology cross. This is the terrifying truth about our size in the universe. Not that we are small, though we are unimaginably, measurably, verifiably small. The terrifying truth is that we are small enough to be permanently confined to one galaxy among trillions, yet capable enough to measure the one next door with extraordinary precision. We can see what we cannot reach. We can calculate what we cannot cross. We can map structures so vast that no journey within known physics could ever traverse them. And we can do it from a room, with a telescope, with mathematics, with the same 3-pound brain that once tracked antelope across the savannah. You are 3 pounds of neural tissue running on the caloric equivalent of a dim light bulb. You live for 80 years on a planet 7,900 miles across, orbiting a star that is one among 400 billion, in a galaxy that is the smaller of 2 gravitationally bound spirals, separated by 2.5 million light-years of empty space. And you measured all of it. The scale is terrifying. The distances are permanent. The isolation is real. But so is the measurement. And there is something in that fact, something precise and irreducible, that no amount of cosmic distance can diminish.